Then I would like to welcome all of you to today's edition of the International Online Seminar on Interval Methods and Control Engineering. And it's my pleasure to have with us today Tarun Pati from the Mechanical Industrial Engineering Department of the Northeastern University in Boston. That's also the university at which he's currently pursuing his PhD degree. And before that, he did his master's studies at the Iowa State University and his Bachelor of Engineering studies at Osmania University in India. And his research focus is on robust and safety critical control, especially with the help of interval methods and set value techniques. And that's also exactly the field from which the current presentation will be. It's about time-invariant and optimal interval observer design via mixed-monotone embeddings. Tarun, the floor is yours.
Hello everyone. Thank you for the invitation for me to present at this seminar. So my name is Tarun Pati, as Dr. Rauf already introduced. I'm a PhD candidate in mechanical and industrial engineering at Northeastern University, working under the supervision of Dr. Shezheng Yang. So today I will be presenting some of our latest works on time invariant and optimal interval observers via mixed monotone embedding. Before getting into the technical details, I would like to motivate our use of this interval observers for state estimation. So to begin with, many modern control systems like autonomous vehicles, robotic systems, and power grids operate under uncertainty, and they need to be reliably operate under these uncertainties because many of them include safety critical applications. So these uncertainties may arise from yeah, these uncertainties may arise from uncertain dynamics, bounded but unknown disturbances and measurement noise, or partially known state or measurement informations. For such systems, point-wise measurements may not be, for example, using classical observers like Kalman filter or Luenberger's observers, may not be sufficient, especially when strict guarantees are required, because these classical observers only provide probabilistic guarantee or statistical guarantees. Instead, what we can do is that we can use set-based or interval observers that provide upper and lower bounds of the state with the guarantee that the true state is always bounded between these two states for all admissible uncertainties. So this approach in particular, when provides us with worst case guarantees under all admissible disturbances. However, exact computation of exact reachable sets are intractable even for simple linear systems with interval or polytopic uncertainty. So some practical methods approximate the sets using interval bounds or ellipsoids, zonotopes, or polytopes. So although ellipsoids, zonotopes, and polytopes are more accurate, they are also more mathematically and implementally complex. Whereas interval observers provide a sweet spot of ease of use and also broader applicability, and also while also providing strict guarantees. So in this seminar, I'm going to go over two of our recent works that we presented in last year's CDC as well as ECC. The first one being time invariant interval and polytopic observers, which was done as a joint collaboration between Feiya Zhu, me, and Dr. Shezheng Yang at Northeastern University. And we presented this at CDC 2025. So polytopic observers, they provide tighter approximations than simple convex shapes, and their implementation and design remains largely unexplored. So some reachability analysis methods do exist, but they lack observer gain design and stability analysis, and most are only applicable for discrete time systems. So when it comes to works related to interval observers, they have been studied very extensively for linear as well as nonlinear systems. These methods usually require error dynamics to be stable and positive or cooperative. So this addition of positivity or cooperativeness either induces like additional constraint that we need for enforcing positivity or cooperativity, or if we design the system to be positive or cooperative by construction, which we did in our earlier works, they induce mixed integer variables in our optimization. So when for the first method that we are focusing on linear systems. So as I've already said, our interval observed methods require positivity and cooperative assumptions. These makes it so that there are no generally guaranteed existence of formal guaranteed for the existence of interval observers even for detectable linear systems. And with this work, that's what we are trying to address. So given a detectable linear system whose dynamics are given here with bounded disturbances and noise, and also with known bounds on the initial state uncertainty, we want to construct an interval observer that is correct. That means the true state is always contained within the our estimated polytope or interval. At the same time, the observer is stable, input to state stable. So, the contribution for this work include introduce a time invariant and potentially a non-square, I mean lifted transformation based on polyhedral diagonal functions. So, where this transformation takes the form of zt is equal to pxt, and p is a potentially a tall full column rank tall matrix. And this transformation takes the form of like P multiplied by A minus LC, P into the closed form state matrix A closed loop is equal to QP, where L is the observer gain. And additionally, this also is designed such that the log norm of Q for continuous time systems is is negative, or the infinity norm of Q for discrete time systems is less than 1. That means Q is contractive, either whether it's for continuous time or discrete time dynamics in infinity norm. So we achieve this by designing mixed monotone embedding based on this polytopic or polyhedral functions and transformations, uh, s- leading to leading to our methods having not require any positive or additional like cooperative constraints. And also we prove like correctness and ISS properties for the set estimates. And as I've already stated, this work guarantees that the time invariant interval observers exist for all detectable linear systems, potentially with having to go to higher dimensions. So to start with, so since A and C are detectable, that means we can always introduce the observer gain L and construct an equivalent system as given here. So, and when we take ACL as the closed loop state matrix, then since it's a detectable linear system, we can design L using any standard optimal estimators such as H infinity optimal observer synthesis. So now our first theorem that we proposed is that for if ACL, this closed loop state matrix, is Hurwitzer sure, and this is guaranteed because A and C are detectable. That means we can construct L such that AC closed loop ACL will be Hurwitz or Schur stable. Then there exists a full rank tall matrix, potentially tall matrix P, and a square matrix Q such that P into P multiplied by ACL is equal to QP, with additional property that for continuous systems, the log norm of Q is less than 0, or induced infinity norm of Q is less than 1. So in P dynamics, and the state matrix Q is contractive. So the transform dynamics are given below. So Z is equal to Px. So when we construct its dynamics, this is the dynamics that we get. Z plus is equal to QZ plus all the terms that are dependent on the output as well as our noise and inputs. And we assume that the inputs are known for this purpose. And this theory only states that there always exists P and Q. And in our lab, we have a algorithm that we use to construct the required P and Q for any detectable, continuous or discrete systems. So existing interval observers mostly require this transformed state matrix Q to be either Metzler or positive, as I've said, for positivity or cooperativeness, and may fail for systems with complex eigenvalues. Uh, but for our from our construction, we don't need to impose Metzlerization of Q or non-negativity of Q. And furthermore, the infinity norm, induced infinity norm of Q satisfies that either its log norm or its induced infinite norm is contractive. That means it decays exponentially. The transformed error decays exponentially. So, as I've said, the transformation P may be of higher dimension M. So, if all the eigenvalues of our original system of the closed loop ACL are real, then we don't need to lift the system to a higher dimension. The transformation can be in the same dimensions as our original state. But if we have like a complex conjugate pair of eigenvalues, then we may it may be required to increase the dimensions of our transform system. So some existing results state that stable time invariant polytopic and interval observers always exist for detectable linear CT systems and DT systems. This we prove by providing an algorithm to compute P and Q for detectable systems. And for more details on this algorithm, you can refer to our like a paper that we presented at CDC. So now that we have our like equivalent system in higher dimensions, which is basically provided here, this system in Z coordinates. So using that, now we can use the embedding system formulation to construct the required interval observer. So Z upper bar dynamics are given, Z upper bar and lower bar dynamics are given here. So the key terms are here, Q up into Z upper bar minus Q low into Z lower bar for upper dynamics, plus all the worst case terms which depend basically on our noise and bounded noise and bounded disturbances. So this sort of construction guarantees that if the initial state Z0 is within this two upper and lower bounds, then for all future times, our future upper and lower bounds always frame our true transform ZT, and without any additional requirements for positivity or cooperative constraints on Q. So now the bounds on using the bounds on Z that we get, we can transform them back to the bounds on X, and consequently we can construct a polytopic bound on X or an interval bound on X, given these two formulations given here. So the first one gives us a polytopic estimate. The second formulation gives us an interval estimate. So this our construction guarantees that by design our systems are correct. That means if we are able to get a stabilizing L, that means a closed loop ACL is Hurwitz or Schur stable, then it is guaranteed that the interval observer is correct. That means the true state is always contained within our polytopic or interval estimates for all admissible disturbances within our bounds, known bounds of noise and disturbance. Additionally, when we compute the error dynamics, if which is defined as the upper estimate ZT minus lower estimate of ZT, then the dynamics for continuous system depend on Metzler's version of Q, or a positive absolute value of Q. And since log norm as well as induced infinity norm do not are invariant under Metzerization or absolute value, so log norm of Q, Metzler's version of Q, is the same as log norm of Q. That means this log norm of Qm is also less than zero. Similarly, the induced infinity norm of absolute value of Q is equal to induced infinity norm of Q itself. That is less than one. So that means this Framer error, which whose state matrix is actually either a Metzler's version of Q or absolute value of Q for discrete case, is also contractive. So that means the error is input to state stable. So to illustrate the effectiveness of our proposed approaches, we use three case studies. The first one is a first one is a simple example with complex eigenvalues whose dynamics are given here. And as we provided the results with the polytopic estimates as well as the interval estimates in the figures given on the right. As you can see, in both cases, our approach with polytopic as well as interval estimates do frame our true states, as well as it is guaranteed that if we start inside this estimate, we're always guaranteed to frame this for all future time. And also we achieved this. One thing I want to reiterate is that we achieved this using a time invariant transformation. Although it may be tall matrix P, but it is time invariant. The second example that we've chosen is a chaotic Showa system whose dynamics are given here. And even in this, it can be seen that our estimates converge to the true estimates pretty quickly, both as for the polytopic estimates as well as interval estimates. So for a discrete example, we've chosen a five-dimensional example from a Meslin paper. So and even in this example, both our polytopic estimates and interval estimates are correct. That means they frame the true states, as well as their volumetric errors are ISS. So to summarize, we propose time invariant interval and polytopic observers uh, for detectable linear continuous or discrete time systems. So we achieved this using potentially non-square, that means P is tall transformation, uh, with P ACL equal to QP, and with the guarantee that Q is contractive. So, and also we circumvented the requirement for extra positivity or cooperative constraints by using mixed monotone embedding techniques. And by construction, our methods are correct, as well as if L is a stabilizing observer, then our interval observer is also ISS. So for future works, we want to extend this to nonlinear continuous time and discrete time systems, as well as for hybrid, more complex like hybrid and switch systems. So now that I've finished with the first part, where we shown that for all detectable continuous and discrete time systems, we can construct an interval observer. So the second part of this talk is going to focus on computation of efficient L1 and H infinity interval observer design for nonlinear systems under bounded uncertainty. And like one key thing is that, as I've said, the main advantages of the first one is that it is applicable for all detectable systems. The second method, although applicable for many nonlinear systems with under uncertain dynamics, there is no formal guarantee that it will work for all. So when it comes to the previous works, so some stable and positive cooperative using positive and cooperative error dynamics, interval observers were built by as early as 2000s and in the early 2000s and even before that, and especially in recent times there have been explosion of many interval observer works depending based on bounding functions and decomposition functions for nonlinear systems. So as I've said, most methods on interval observers need either extra positivity or cooperative constraints, which can lead to extra conservativeness. So our prior works try to reduce this conservativeness by designing interval observers such that by construction they are positive or cooperative. So there is no additional requirement of positivity or cooperative constraints. But this comes with the cost that our optimization will have mixed integer terms in the optimization. So which is not an easier problem to solve. So we what we want to do with this work is that try to eliminate that mixed integer terms from our optimization so that we can either have a simple linear program or a bilinear program. So building on an earlier work, we propose a new design with efficient gain computation. By efficient, we mean that we are replacing mixed integer optimization with either linear or bilinear optimization. So they are easier and faster to solve, and more solvers are applicable. And also, we want to introduce a new improved bounding for continuous time systems uh, using a continuous time reminder form decomposition function that we proposed in this work. So we also finally want to validate our results using certain case studies. So to begin with, I want to introduce certain key definitions that we use throughout this work. The first one being that of mixed monotonicity and decomposition function. A function f is mixed monotone if a corresponding decomposition function f delta or fd exists, such that fd is function of twice the number of dimensions of f with three conditions. The first one being that if the first n set of states and the last n set of states of fd are equal, or f x and x, then we recover our original function f of x. And it is monotonically increasing in its first set of variables, first n set of variables for discrete case, and for continuous case there's a small variation. And the third condition is that it's monotonically decreasing in its its last n states. And using this decomposition function, we can, for any given n-dimensional system, x plus equal to g, and with corresponding decomposition function gd, we can construct an embedding system as given by equation 1. And this embedding system has a state frame property, i.e., if initially the true state of our original system is bounded by the states of this embedding system, then for all future time, the states of this embedding system will also frame the true state. So now that we have our preliminaries, so I would like to introduce the system that we are focusing on, which is a nonlinear system as given by equation 2, and we are assuming that the noise and errors enter the system affinely, as well as they are bounded with known bounds. So as I've said, the first assumption is that the bounds on noise and disturbance are known, as well as the initial state bounds are known. And we also assume that at any given time t, the output yt as well as ut are known. So, and also an additional assumption that we make is that the mappings f and h, the nonlinear mappings f and h, are locally Lipschitz differentiable and mixed monotone in their domain. and also have known Jacobian bounds. So now that we have our preliminaries and the system description, we would like to present our some important definition. First one is definition of correctness, which basically means, as I've said, the true state is always framed by the R estimates. And the next definition is of stability, which is basically either the observer or proposed observer is L1 or H infinity optimal. So now we can state the problem that we are trying to solve as given the system that we description in two that satisfies our two assumptions. We want to design an interval observer that is correct, that is stable, uh, and also it does not involve any mixed integer programming. That means our observer is computationally efficient. So as I've said, we are introducing a new continuous time decomposition function. So basically, what we're doing is trying to do is that given a vector valued function f for continuous time system, we are introducing off diagonal Jacobian sign stability, which simply states that the Jacobians of f within our known domain are Jacobian sign stable only in their off diagonal elements. So the diagonal elements of the Jacobian need not be Jacobian sign stable. So by Jacobian sign stable, I mean that within our domain of X, the Jacobians, each elements of the Jacobians have stable signs. So using this off diagonal Jacobian and stable decomposition functions, we can construct a corresponding decomposition function as given here, with the guarantee that when the uh, upper estimate of using this decomposition function minus the lower estimate of using the decomposition function is always bounded by this linear term as given here. So now that we've introduced our off-diagonal Jacobian signs stability as well as how to construct a corresponding decomposition function, we introduce first what we first do is that given any nonlinear function f, we don't know if it's like Jacobian sign stable or off-diagonal Jacobian sign stable. But for any Lipschitz continuous function f, we can always divide that into a linear component hz and a nonlinear component mu z, such that mu is either JSS or OJSS. And how to construct this h, the linear remainder h, we detailed in these 2 points given below. So now that we have now if we can as I've said, if we can divide a function g into its linear and nonlinear components, and by individually bounding this linear and nonlinear components, we can construct a corresponding decomponent function for the original function g. So these first two terms bound the linear part of the function, and this decomposition function mu d is used to bound the nonlinear component. So in this approach, similar to our earlier methods where we also uh, constructed interval observers that do not require any positivity or additional cooperative constraints, even here we use a multi-gain structure uh, using the equation t plus nc equal to I, where t and n are additional gains that we introduce on top of the observer gain L. So in this construction, we have three gains T, N, and L. That means we have additional knobs to tweak so that our observer to get like desired results for our observers. And in this case, in this work, to have the ability to uh, avoid like mixed integer formulation, we introduce we split each gain that we have like T, N, and L into two additional gains. For example, for t, we split it into t positive minus tn. So tn and tp and tn are basically element-wise positive matrices, and it is a known fact that any matrix, given any matrix, we can always split that into a difference of two matrices, two positive matrices. And using that idea and the transformation t plus nc equal to I, we basically construct we reformulate our dynamics into a new coordinates using these reformulation equations. And finally, we basically get a equivalent system in the new dynamics using the transformation t plus nc. And on what we do is that we construct our interval observer based on this new transform dynamics, and the observer dynamics are given in equation 7. Interval observer dynamics are given in equation 7. So the key thing is that in this, the state matrix mx and m, uh, m mx for both discrete and continuous case, we use our we split it into like a positive and negative parts for discrete case. Or for continuous case, what we do is that we split it into like first split it into diagonal components and non-diagonal components. And for the non-diagonal components, we also further split it into positive and negative components, and use those splits to construct our interval observer. And why we do that is that this type of construction guarantees that by design our interval observer is correct. And now that we've like enforced correctness using like our design method, now the second thing we need to do is that we need to enforce stability. So for this purpose, we need to design our gains T, N, and L to satisfy some kind of like optimality. So first optimality that we chose is L1 optimality, and that is gained by solving equation 10. And the solutions for this basically give us our three required gains T, N, and L, and using that our observer is L1 optimal. And as I've already stated, this is not a new result. This was already, we already had this result in our previous works. The only difference being that in our previous works, our optimization had like mixed integer terms. And in this work, which will, we will circumvent the presence of this mixed integer terms, which will explain in the next subsequent sections. So we also included like a second optimal interval observer design, HNPT optimality, for and which looks like equation 11 for discrete time systems, and for continuous time system it looks like equation 12. And one thing to note is that in both the L1 case as well as in H infinity case, for the continuous time systems, we have bilinear constraints or bilinear programming. And before in our earlier works, it was even more complex that we had mixed integer bilinear programs. So now, by eliminating like mixed integer terms, we are able to reduce it down to like simple linear or bilinear programs. So as I've said, we are trying to circumvent the presence of mixed integer terms or absolute value terms. So using the interval observer that we presented previously, if we construct the Framer error basically reduces to the simple linear comparison system as given here, where all the matrices AX, AW, AV, and AU are linear matrices, but they involve absolute value terms of our constraints L, T, and N. So, which is undesirable for which is what we are trying to prevent. So, the key idea that we use to achieve this is that we can always upper bound an absolute value term of a matrix as given here. So given any matrix mx, uh, its absolute value can be bounded above by sum of two positive matrix APX and APN, and this APX and APN are such that when as I've already said with our T, their difference gives us mx or the original function mx, and their summation gives us the upper bound on the absolute value matrices. And we use this trick to basically bound all the absolute value terms or replace all the absolute value terms in our equation. So in this error dynamics, we have absolute value terms in all the matrices, right? And all these absolute value terms, we replace them with these linear terms. Basically, the only caveat is that we always we need to increase the number of terms to twice the number of terms from before. So for each absolute value term, we need to introduce two copies of additional terms to make them to remove the absolute values. So now that we've removed the absolute value terms using the trick that I shown in the previous page, what we apply like similar arguments in our previous papers to enforce stabilization. So we basically use standard L1 optimal or H-infty optimal uh, uh, stabilization techniques in literature to achieve stabilization of this error comparison system given below here. And by using the standard optimization techniques, we basically achieve our required gains. As I've said, instead of having only T, N, and L, the multi-gain design that we designed previously, for each T, we have two, TP and TN, and LN and LP, as similarly for N, NP, and NN. And which is basically required to eliminate all the absolute value terms. And to show the effectiveness of our proposed approach, we've taken two case studies. The first one is a continuous time case study whose dynamics are given here. And from the results, it can be seen that the proposed framers do guaranteedly bound our true state, and also they converge to the true state faster than our earlier approaches, as well as some standard interval approaches in literature. And for the discrete time example, we have chosen a discrete time chaos enhanced system as given here. And even in this example, it can be seen that the new estimates from our new approach match or improve upon L1 or H-infinity observer designs that we had previously, which involved mixed integer terms. And also, they're better than the methods provided in some standard interval observers literature. So, and to also show, visualize how much of an improvement this removal of mixed integer terms is, we've also computed the CPU runtimes for the proposed the new approach as well as our old approach, and we compared the CPU runtimes. And in both the H infinity and L1 observer case, the new proposed L1 and H infinity methods solve gain computation much faster. This is especially true if the system states, the original system states, are of higher dimension. So for lower dimensions, the advantage may not be as prominent, but the more you increase the dimensions, the more apparent the advantage becomes. And by avoiding this as a state integer variables, we have significantly less CPU cost. So to conclude, so we proposed computationally efficient extensions of our previous L1 and H infinity interval observers. We achieved this by reformulating mixed integer programs into continuous optimizations. We additionally retained our multi-gain structure, and also the positivity and correctiveness by design. And also we used the L1 optimal and H infinity optimal designs to make the estimation error uh, input to stage table. We also developed a tighter continuous time decomposition function, and we also showed that our new proposed methods have comparable or better performance to our old approach, which involved absolute value terms. And for the future work, we want to extend these to systems with unknown inputs. So, as I've said, in this work, in both these two works, we assume that the inputs are known at any given time t, and we want to extend both these works to systems with unknown inputs as well as generalize to hybrid systems with jumps. So this concludes my presentation of two topics. The key takeaways here being that in the first method we proposed a time invariant interval observer, and we showed that such observers exist for all detectable linear systems, which is a nice guarantee that classical observers have for linear systems. And we extended that formal guarantee to interval observers existence as well. And with the second method, we've shown that using mixed monotone embedding systems, we enables us to construct interval observer designs for nonlinear systems without requiring additional like positivity or cooperative constraints. And also, our new formulation removes any mixed integer terms present, making the optimization computationally efficient. Uh, and with this, I would like to conclude my talk and thank you for your presence for my presentation. And I would be happy to take any questions.
Okay, many thanks, Tarun, for your presentation, and I'm pretty sure there will be questions. Who wants to start? Okay, no one has unmuted him or herself, but I can start in any case. Could you go back to the slide 44,
Okay.
where you had the last example?
Is this?
That's 47. Yeah,
Okay.
this one here.
Okay.
Let's go back to the previous one where you have the state equations. What we can see here is, especially in the state equation for x3 dot, you
Yeah.
have this multiplicative coupling of a cosine function and x2.
Yeah.
Yeah,
So,
and in many cases, maybe let me just continue. What could be done there in such cases is you cannot only exploit this mixed monotonicity property that you did, but what
yeah.
you could also do is you could factorize the equations in such a way that this cosine of x1 becomes a coefficient of x2 in a dynamics matrix, something like a quasi-linear state space representation. And then you could bound that coefficient, for example, by an interval plus minus 1. Do you have any general guideline in which, from which you could say, for example, that bounding such terms with a priori given information, in this case, cosine function, that's easy. You could also do the same thing with the sine function. You could rewrite it as sine of x1 divided by x1. This thing is always also bounded, yeah, finitely. When such kind of bounding approach is more efficient and when the mixed monotonicity approach is more efficient? Or do you suggest to try out from application to application?
So at least in our lab so far, what we've done is that we've tried out for application to application, primarily using the mixed monotone embedding method to bound.
Mhm.
So and also for this specific example, we have this one advantage that, as you can see, we are measuring the output x1. So any nonlinear function of
Yeah.
x1, we can also consider it as a measured thing. So we can
Yeah,
just like
that's a bit of cheating here in this
yeah,
example.
it is a cheating, but I mean, we also have the results without assuming that sine of x1 is a measurement. So in both the cases, we are getting interval observers, and the only advantage is that by assuming that this one is a measurement, the interval observers are more like accurate. So
Yeah.
that's how I can put it. Yeah.
Yeah. And the other question that I have is concerning this comparison. What you mentioned, you mentioned you compared it with a work of Tucked In from
Yeah.
2020, 2014.
Yeah.
Which type of observer did Tuck use in this case? Is it an extension of a Lüneberger observer as an interval framer, or was it an TNL observer? Do
Uh,
you know that?
it's it's
Otherwise, I have to look it up.
yeah. I may have to look it up. So it's 1 minute. Yeah. L- it's a extension of a Leuenberger observer. Yeah.
Okay. Yeah. That means maybe it would also make sense for such systems where this extension of the Lüneberger observer exists. There exists also this TNL extension.
Yeah.
Yeah, and then I think it would also be nice to see the compromise. When is TNL more efficient and when is your approach more efficient?
Yeah. I agree. Yeah.
Yeah. Yeah, and the last question that I have, or no, second but last. Um, Uncertainty in the output equation. Did you try in any of your application scenario to design some framer, some interval observer for the case that the coefficient in the output vector C are uncertain? Because
Uh,
then you also have a big challenge. You either have to map this to, let's say, design matrix inequalities. This would be
yeah.
one thing. Or the other thing, you could shift it into the noise term V.
I mean, that's what we basically do. We not either normalize C or do something else to make it so that we assume that the matrices V are like that multiply the noise are constants, and
Mm,
all the uncertainty goes into our noise itself.
yeah. Yeah, and there are some examples. I can forward you an example that one of my PhD students is working on. That's in the frame of state estimation for battery systems. And
Okay.
there the output equation is nonlinear. And then the
Okay.
question is how to do this. You could over approximate this, for example, by
So
an
although we
uncertain
don't,
coefficient vector in the output, or you could shift it to the noise. Yeah, and it depends on the parameterization of such systems. Partially, for example, you're losing if you're doing it in a non-efficient manner, let's say it that way, you may lose observability or detectability of this over-approximating system, although the underlying nonlinear one is observable.
yeah, that is true. Yeah. So that is true that like we have this issue that we may lose existence. I mean, the problem may be infeasible, may become infeasible. Yeah.
Yeah, and it's especially challenging if the output equation is nonlinear.
So that is true, but our methods do apply. I mean, at least the equation is linear, sorry, non-linear in the state. We have methods to. I mean, our current methods do work if it's non-linear in the state, and also we have an extension where if the disturbance in the state W, if that is also nonlinear, enters nonlinearly, we can still like use our methods to construct an interval observer. The only thing we haven't been able to figure out is if the like measurement noise V, if that comes in non-linearly, then we haven't been able to figure out like how to construct interval observers.
Okay. Yeah, and then my last question, at least, is you mentioned in the outlook that you want to handle the case where you have unknown inputs.
Yeah.
Do you want to assume given bounds on the unknown
Yeah,
inputs, or do you also
without
want
bounds,
to
like yeah,
estimate the
it's impossible.
bounds?
Like if we assume minus infinity plus infinity, so it is impossible. So we assume that bounded inputs, but unknown. Yeah.
Yeah, no, the reason why I'm asking this is,
Actually, let me correct it. I
yeah,
guess
okay,
we have other. Sorry, I'm young here. I guess.
yeah,
I guess we have other works that also can do unknown input observer without assuming bounds on the unknown inputs, but it relies on the structure of the dynamical system to give us additional information for us to do it.
yeah,
So, yeah, just wanted to add that. But that's not Tarun's work.
yeah.
It's some other students' works, and we have looked at it before.
Mm. No, the reason why I asked this question is I think it is especially of interest in case where you want to do, for example, also system identification, where you want to estimate this unknown input.
Yeah.
And yeah, such identification tasks definitely also, yeah, are highly relevant in practical applications and also from time to time very challenging.
Yeah.
Okay, further questions? Fabian.
First of all, thank you, Tarun, for this talk. I have a question regarding your first part,
Yeah.
and you introduced this state transformation, and I'm wondering, in which cases is this transformation possible, or are there cases in which is it not possible?
So this transformation is always possible if we have a detectable pair of A and C. So for any detectable linear system, we can always construct a transformation P ACL equal to QP.
Okay, do you have any method how to find this?
We have an
P?
algorithm that
Yeah.
we use to construct like P and Q, and the details of this algorithm can be found in our paper. Yeah.
Okay, thank you. Then I will have a look into your paper.
Yeah. I mean, that's the the primary advantage is that this is applicable to all detectable linear systems. And also we have a like algorithmic way of finding P and Q.
Okay, yeah, great, thanks.
Okay, further questions? Really, the last chance for final questions? If there's no further questions, again, many thanks, Tarun, for your presentation. And yeah, I have 2 points for advertisement. Firstly, and this will also be included in the next message that I send around, there are 2 events that may be of interest for the interval estimation community. One is we're organizing a spring school on set-based methods at the University of Oldenburg from the 20th to 24th of April. I think that's especially of interest for people in Europe. And there will be a pre-conference workshop on set-based methods at the European Control Conference in Reykjavik. It has been accepted yesterday, and we'll also send around the corresponding information within the next email newsletter in the frame of this online seminar. And then the last advertisement will be related to the next presentation in this online seminar. It will be on the 10th of April, and Laura Lützow, who is also present here in the audience, will then present her research activities. And yeah, from that point of view, many thanks again, Tarun, for your presentation. Many thanks for all participants. And yeah, have a nice weekend and see all of you soon.
And thanks again for the invitation. Yeah.
Bye.